Hi, I'm Anna, and this is my video for Lab 5, Faraday's Law. Introduction. The background to this lab was that Faraday's law relates a magnetic field varying with time to an electric field whose path integral around a closed path provides an EMF that's able to produce current. The induced current due to the aluminum foil generates a magnetic field that exerts a force on the source of the magnetic field, which in this experiment was the falling bar magnet. The goal of this lab was to obtain observational data about a magnet falling through a conductive tube made of aluminum foil, to model the magnet and tube interaction on Python, and to compare the computational results with those obtained. The fundamental physics principles I used in this lab were Faraday's law, the Biot-Savart law, and Ohm's law, all of which are shown below. A summary of my results were it took 1.9 seconds for the magnet to fall in the video experiment and 1.71 seconds for it to fall in the simulation. Experimental procedure. The supplies needed were a roll of foil, with the foil being around 1 centimeter thick, a magnet, a phone, and a ruler or meter stick. The first step was to determine the north pole of the magnet using the magnetometer app from Lab 3. And then after that, the second step was to drop the magnet through the foil tube and determine how long it takes for the magnet to fall through the tube. This was repeated 5 times to determine an average time. And then a video was recorded of the magnet falling through the aluminum foil tube. So the data taken, the length of the tube I used was around 30 centimeters. The width of the foil on the tube was around 0.9 centimeters. Radius of the tube was around, the full tube was around 2.25 centimeters. The mu I used in this lab was 1.93. Mass of the magnet 23 grams, and the average time it took to fall was around 1.9 seconds. And here's my video. So here's the code I used in this section, just mostly the physical constants, and then start some code to start the graph. And here's where I input the data I took. In this section, the tube of aluminum foil was created as a series of rings along the y-axis. Along with the bar magnet was also created with a mass and the mu used in Lab 3. In this section, the magnetic field was created and the magnetic flux was calculated, and a loop simulation was also created. In this section, the final section of the code, the magnetic force was calculated from the magnet, as well as magnetic force on the magnet, and F net was summed up as F grab plus F magnetic, and the function was used to calculate the time in tube in seconds. So my model and calculations, the time in tube calculated by the simulation was around 1.71 seconds. This here is the graphic created of velocity versus time, and here is the screen recording of the simulation as it moved down the tube, in which the red is the clockwise current and the blue is the counterclockwise current. And as such, the magnitude of the currents are represented in the intensity of each color. This is a little bit of a long video, so for time, I'm just going to skip ahead. Interpreting the simulation, as I said before, red is the clockwise current and blue is the counterclockwise current. As the magnet falls downwards, the change in magnetic flux is increasing in the negative y direction, so the induced current is acting counterclockwise to oppose this change in flux. When the magnet is flipped around, however, it still falls downwards, but the magnetic flux is now increasing in the plus y direction, so the induced current moves in a clockwise direction as opposed to counterclockwise. The differences in experimental and computer simulation data I will discuss in the conclusion. The shape of the velocity versus time plot tells us that the force acting on the bar magnet eventually sum to a net force of 0, as shown in this plot when the velocity reaches a flat line. It is constant. The final velocity, which is constant for the remainder of simulation, or until the magnet leaves the tube. Questions and conclusions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the bar magnet change? So due to Ohm's law, the induced currents would be larger if the resistivity of the conductor was 0. Due to this, the magnet's fall would take a longer time. What if holes, slots were cut into the tube? How would this affect the ring currents in the model? The magnetic force would decrease, so the induced magnetic field would be weaker. Because of this, the magnet would fall faster than if there were no holes or slots. Conclusions. The time taken for the magnet to fall through the tube in the experiment was around 1.9 seconds, whereas the simulation calculated it to be around 1.7 seconds. So in order to find the difference between these two, I calculated percent error, which of course is experimental minus the model over the model. Basing on the model is the more accurate time. So I found that there was a percent error of around 11%, and this could be due to errors in the magnetic dipole moment mu, which were calculated in Lab 3 previously. So that is the end of my lab. Thank you for watching.